Okay, so this is going to be a brief review of atomic theory. I'm going to try to do it as quickly as possible, but it would still probably take me at least 20 to 25 minutes. Let's get started. The first thing that we should start with are the scientists that have contributed to our modern day atomic theory. So we are going to go all the way back to, we have Democritus, who is Greek, who said that the atom was a hard sphere, coined the name atomos. Followed by him was Dalton, and this is the cannonball model. Agreed that atoms were indivisible, and he came up with the name atom, I believe using Democritus's word atomos. Then we have J.J. Thomson, with the plum pudding model. And he used the cathode ray tube and found out that electrons were negative. And what he said was that if you imagine the atom, you have all this positive charge, and he said that the negative charge was then evenly distributed within that positive charge. So he said the positive and negative were basically mixed together. Then came Rutherford, and I will go over this with the gold foil experiment. And what Rutherford did was he projected alpha particles at a piece of gold foil. Alpha particles are positive. They are actually the nucleus of a helium atom. And what he found out was that most of the alpha particles went straight through, as I showed you in the video, and only a couple were deflected back. This led him to two conclusions about the atom. And the first one was that the atom is mostly empty space, and that's because most of the alpha particles went straight through the gold foil. The second thing he concluded was that there must be a small, dense, positive center, which we now call the nucleus. And that is because the only reason why something would be deflected back was if it met something of similar charge. So alpha particles are positively charged, therefore they must have contacted something positive. They were deflected away from that positive charge. After Rutherford, we had Niels Bohr. That's also referred to as the planetary model, in which he said that electrons orbit, if this is the nucleus, in distinct paths. And then lastly, we have the wave mechanical model, or which is sometimes referred to as the cloud model. And Schrödinger put in a lot of work toward this new model, in which electrons have both particle and wave-like characteristics. And what he said, or what, was determined, was that an orbital is the probable location of an electron, because electrons are constantly moving. So that's the sequence of scientists. And you can look at your notes just to go into a little bit more detail with them. I just told you I was just giving you a very, very brief overview. So let's talk about the structure of the atom. When you see the words subatomic particles, that means that we are referring to protons, neutrons, or electrons. When you see a question that says, explain in terms of subatomic particles, somewhere in your answer you better be talking about protons, neutrons, or electrons, depending on what the question is. So we have the atom, and it has a nucleus which contains the protons and the neutrons. Protons have a positive charge, neutrons have no charge. Protons have a mass of 1 AMU, and neutrons have a mass of 1 AMU. Then we have the electron cloud, which contains the electrons, which are negatively charged and for all intents purposes have 0 mass. Now there's a couple of words that are really important when we're talking about atomic structure. One is nucleons. Nucleons refers to what's in the nucleus, so we're talking about protons and neutrons. And also the term nuclear charge. When it asks you what is the nuclear charge of fluorine, the nuclear charge is +9, because nuclear charge really equals protons. Because when you think about nuclear, the only two things in the nucleus are the protons and the neutrons. And the neutrons have no charge. So really this is just a back way of asking you what is the number of protons of fluorine. And they will do that. So you need to make sure that you know that. Now, I went over this in the video lessons. Table O are symbols used in nuclear chemistry, and we will use them when we get to the nuclear chemistry unit. But you can also use them for atomic theory, and I'll tell you why. Because if you forget what a proton is, it's right here. It can be written as 11H or 11P. Remember that this top number refers to the mass. This bottom number refers to the charge. So when I ask you for the mass of an electron, it's right here. An electron is also known as a beta particle. It has a charge of 0. I mean a mass of 0. It has a mass of 0 and a charge of -1. If I ask you for the mass of a neutron, it is right here. It's a mass of 1 and a charge of 0, which makes sense because we know that neutrons are neutral. Here are the alpha particles. You can see that this is a helium nucleus, or it could be written like this. They are positively charged. How do I know? Because this plus 2 is the charge, and it has a mass of 4. These other ones we will talk about when we get to nuclear chemistry. Let's see what we can determine when we look at the box of an element symbol. Well, this number is the mass number. This number is the atomic number. And that equals the number of protons. It also lets us know the number of electrons, because in a neutral atom, protons equal electrons. Protons equal electrons. This is the electron configuration. The last number is the valence electrons, the electrons in the outermost shell, and everything before it is considered the kernel, the inner electrons. These are the various oxidation states. Meaning the charge an atom will have when it gains or loses electrons. And then it becomes an ion. So let's look at this top one as an example. -3. If I say N -3, what that means is it has gained, because electrons are negative. And when I gain negative charge, I become more negative. So nitrogen has 7 protons. If it has a -3 charge, that means it now has 10 electrons, because a +7 and a -10 gives me a net -3, and that's where this charge is coming from. And if I wanted to know the number of neutrons, remember that neutrons equal the mass number minus the atomic number. So I've got a mass number of 14. We always round up or round down by looking at what the 10th place is. -7 equals 7 neutrons. I think that's all of the information that you can get from an element symbol. Let's talk about average atomic mass. When you look at I want to go back 1 minute. This is important. I would think everybody would know this, but I'm going to say it anyway. The atomic number identifies the element. That is its identifier. Your fingerprint identifies you. The atomic number identifies the element. Okay, average atomic mass. is the average mass of all of the naturally occurring isotopes of an element. So when we look at the atomic table, when we look at the periodic table and we see carbon has a mass of 12.011, this mass represents the average of carbon 12, carbon 13, and carbon 14. Remember how we calculate average atomic mass. The easiest way is to take the percent abundance times it by the mass of the first isotope, so iso number 1, plus the percent times the mass of iso number 2. And you can keep doing this dot 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 for however many isotopes there are, and then you divide the whole thing by 100 to get rid of the percent. The other way, as I told you in class, is to just take the percent out of percent form and just use the decimal. But we talked about the problems with that if you have small numbers. So if you have 5%, then that really equals 0.05 as a decimal. So if you're not going to remember to move the decimal place 2 places to the left, okay, then you don't want to do this. That other way that I showed you was decimal times mass of iso number 1 plus decimal times mass. And here you don't divide by 100 because you've already taken it out of percent form. And you would do this for however many isotopes you have. I think this is the preferred and best way not to make any errors. So if I were to do an example of this, and let's say I had 2 isotopes, neon 20, which was 95% abundant, and neon 21, which was 5% abundant. So to solve this, I would do 95 times 20 plus 5 times 21, and then divide by 100. And you should get 20.05. This is the average atomic mass. This mass represents the average of neon's naturally occurring isotopes. Now, another thing that I want to point out here that should make sense to you, do you see what this average is closest to? It's closest to neon 20. And that should make sense because this one was 95% abundant. We had more of this in nature than we did 21. So you can look at isotopes. I can have the 3 isotopes of hydrogen. And this one might be 90% abundant, this one might be 7% abundant, and this one might be 3% abundant. Well, before I even do any math, I know that my average atomic mass is going to come out closest to 1, not 2 or 3, because this is the one that's present the most, 90% of the time, or 90% in nature. So let's look at the formal definition. I'm going to finish up with the formal definition of an isotope here. An isotope has the same atomic number but a different mass number. How could I rewrite this definition in terms of, I'm giving you a directive, subatomic particles? That means in my answer, I better be mentioning something about protons, neutrons, or electrons. Those are subatomic particles. So to rewrite the definition, an isotope has the same number of protons, because that's what our atomic number tells us is the number of protons, but a different number of neutrons. And I know this because the mass number is made up of only P plus N, because electrons have no mass. So if I'm telling you that the protons are staying the same, then the only thing that can be different is the neutrons. Okay, let's talk about ground state versus excited state. This is found on the periodic table. Not found on the periodic table. Electrons are in the lowest energy levels. Electrons jump to higher levels. So, for example, sodium 281, ground. Sodium excited 272, or 182. Remember that ground state, number of ground state electrons equals number of excited state electrons. I had 11 here, I have 11 here. Another thing that you need to remember is what's happening with the energy. When you go from low level to a high level, energy is absorbed. And then when you go from high to low, energy is released in the form of visible light. Which we refer to as spectra. And remember that spectra for an element is unique, okay? Each element has its own spectra, which is specific to it. That's why scientists can determine what gases are present in stars. Okay, let's talk about, let's see what else I forgot. Lewis dot diagrams. Lewis dot diagrams. It's the chemical symbol plus valence electrons. No more than 2 on each side. So let's do 2 of them. Let's do aluminum. Aluminum has 3 valence electrons, 2 on top, and then we go round robin. Neon, 8, 1, 2, 3, 4, 5, 6, 7, 8. If I have F minus, and my electron configuration for fluorine is 2, 7, this means that it gained 1, and it is now 2, 8. So that means it's got 8 in its valence shell. So 1, 2, 3, 4, 5, 6, 7, 8. This is an ion. It must be in brackets and show charge. Another example of an ion would be sodium, 281. But if it becomes a positive ion, it means it's going to lose 1. I'm going to just write this a little bit different. Just give me 1 second. Okay. I'm going to write that as F going to F minus. And this is Na going to Na plus. Just to make it more clear. So now it's only 2, 8. So its outermost shell actually has 0. So we don't put any dots around it. It's empty. We just put it in brackets with charge. Remember that when we form an ion, it is a positively or negatively charged atom based on the gain based on the loss or gain of electrons. So we're going to learn this a little bit later on, but metals tend to lose electrons and form positive ions, which are called cations. I gave you the expression, are you positive you lost the cat? Because cat and positive remind you of cation. When you lose, just like losing weight, you become more positive and you get smaller. Nonmetals tend to gain electrons and form negative ions. Because when you gain weight, you become more negative and you get bigger. So think of weight loss and weight gain in terms of electrons, and it might help you remember it. The last thing we are going to go over is Bohr diagrams, which is just a model to help us look at the arrangements of the protons, neutrons, and electrons. So again, let's use sodium. Has an electron configuration of 281. Has 11 protons. I think it has a mass of 23. Okay. So if I'm drawing a Bohr diagram, I have my nucleus. So I'm going to put 11 protons. 23 minus 11 is 12 neutrons. Take the atomic mass minus the atomic number, get the number of neutrons. 281 tells us that it has 3 principal energy levels. And it's got 2 in the first, 8 in the second, and 1 in the third. Now you can also draw it as I did in class like this, but it really takes a much longer time to draw the whole thing. 2, 8, and then 1 in the last one. So I told you that you could just simply do these half shells. How do we figure out how many electrons are in each principal energy level? Electrons in principal energy levels. We use the formula 2n squared. So if I'm talking about principal energy level number 3 and I want to know what's the max number of electrons that I can put in principal energy level 3, I do 3 squared, which is 9, times 2, which is 18. So this can hold a max of 18. Principal energy level number 4, I would do 4 squared, which is 16, times 2, which is 32. We can work backwards here. Principal energy level number 2. So I've got 2 squared, which is 4, times 2, which is 8. And principal energy level number 1. 1 squared is 1, times 2 is 2. So this is the max number of electrons in each principal energy level. Okay, please work on the practice test, and if you come up with something that you don't understand, please bring it up in class. And that was a brief review on atomic theory.